Mr. B here. Matter is composed of tiny particles called atoms. Atoms are composed of even smaller particles, protons, neutrons, and electrons, collectively known as subatomic particles. In this video, I will explain how the subatomic particles will come together to form the structure of an atom. All atoms, with the exception of one isotope of hydrogen, contain the following subatomic particles: protons, neutrons, and electrons. The masses of these particles may be indicated in two different ways: the AMU or grams. In terms of AMUs, the mass of one proton is equal to 1.0073 AMU. The mass of one neutron, 1.0087 AMU. And the mass of one electron is 0.0005486 AMU. Another way to indicate the mass of an electron is as follows, where simply divide 1 by 1,836 and multiply that value times the mass of one proton. In other words, the mass of one electron is equal to the mass of one proton divided by 1,836. Most people are familiar with the concept of the gram. However, what is an AMU? An AMU is a unit of measurement that relates the mass of the carbon-12 isotope to the mass of a subatomic particle. 1 AMU is equal to 1/12 times the mass of the carbon-12 isotope, where the carbon-12 isotope is exactly 12.000 AMU. Unfortunately, the use of atomic mass units, or AMU, is problematic in terms of the actual masses of the various isotopes. Consider the isotope of carbon-12, where the mass of carbon-12 is known to be 12.000 AMU. The nucleus of this isotope contains 6 protons and 6 neutrons. If this is true, then multiplying 6 times the mass of one proton plus 6 times the mass of one neutron should equal the mass of the carbon-12 isotope. However, the actual mass in AMU of the carbon-12 isotope, assuming that the total mass of the subatomic particles are used, will be 12.096 AMU. So the question becomes, what happened to the missing 0.096 AMU? And the answer is that during the formation of an atom of any element, some of the mass is lost or converted into energy. This concept is known as the mass defect. During the formation of the carbon-12 isotope, because of the mass defect, 0.096 AMU of matter was converted to energy. This resulted in a loss of about 0.79% of the atom's mass. The concept of the mass defect is easier to envision if I use grams instead of AMU to demonstrate the mass of the isotopes. Consider the element potassium, where potassium contains 19 protons and 20 neutrons in its nucleus. The mass contribution from the protons may be calculated as follows. 19 times the mass of the proton, which is 1.673 times 10 to the minus 24 grams per proton, times Avogadro's number, which will indicate the number of particles per mole. Avogadro's number is 6.022 times 10 to the 23 atoms per mole. And after performing the calculations, the mass contribution from the protons should be 19.142 grams per mole. The contribution from the neutrons may be calculated in a similar fashion. 20 times the mass of a neutron times Avogadro's number is equal to 20.174 grams per mole. The sum of these two masses should give the mass of the isotope, where the sum of these two masses is equal to 39.316 grams per mole. Unfortunately, although potassium forms about 25 or more isotopes, no isotope has a mass of 39.316. Therefore, during the formation of the potassium-39 isotope, some mass must have been lost. Keep in mind that the actual mass of an isotope will always be less than its isotopic notation. In other words, although this information pertains to the potassium-39 isotope, the actual mass of this isotope will always be less than 39. Okay, now we know the mass and location of the various subatomic particles. We also know that during the formation of an atom of any element, part of the mass is converted to energy. Now let's turn to the periodic table to learn how to construct diagrams of atoms of the various elements. A simple way to illustrate the structure of an atom is by using a Bohr model. This is a simplified example of a Bohr model, where a Bohr model contains a central nucleus surrounded by energy levels. These energy levels represent the location of the electrons, and of course the nucleus represents the location of the protons and neutrons, and therefore by default the location of the majority of the atom's mass. To construct a proper Bohr model, simply use the information provided on the periodic table. Let's return to our example of the element potassium. On the periodic table, potassium is listed at a mass of 39.0983. And of course, potassium contains 19 protons, so the atomic number of potassium is 19. For any neutral element or atom, the number of protons and number of electrons are always equal. So an atom of the element potassium contains 19 electrons. But these electrons are arranged in a specific pattern. This is known as an electron configuration. And the electron configuration for potassium is simply 2881. To construct the Bohr model of this element, simply draw a nucleus and place the 19 protons inside of the nucleus. The number of neutrons is determined by subtracting the number of protons from the rounded atomic mass. 19 from 39 is equal to 20. So this atom contains 20 neutrons. The number of energy levels, or shells, may be determined in two different ways. First of all, potassium is found in period 4 on the periodic table. This indicates that an atom of this element will contain 4 shells. Alternatively, simply observe the electron configuration, 2, 8, 8, 1, where each number is separated by a dash. There are 4 numbers here. This implies that each number represents the number of electrons located on a specific shell. The number of valence electrons, where valence electrons are located on the outermost shell, may be determined either by observing the electron configuration, where the last number is 1, or by locating the group in which the element is found. Potassium is found in group 1, so therefore an atom of this element will contain 1 valence electron. A much less detailed way to illustrate the structure of an atom is by using a Lewis structure, or a dot diagram. To write a dot diagram, simply write the symbol of the element. In this case, K for potassium, Br for bromine, or Kr for krypton. And then simply indicate the number of valence electrons. K is located in group 1, therefore K possesses 1 valence electron. Br is located in group 17, or 7A. Br will possess 7 valence electrons. And Kr, which is located in the noble gas column, group 8 or 18, will possess 8 valence electrons. Now let's apply what we've learned so far to a real-life situation. Suppose it was known that there were 3 isotopes of magnesium: magnesium 24, magnesium 25, and magnesium 26. And that the actual masses of the isotopes were 23.985, 24.986, and 25.983. Notice that the actual mass will always be less than the mass indicated in the notation of the isotope. In other words, magnesium 24 will have an actual mass of 23.985. And remember, the mass that is missing was lost due to the mass defect. Relative abundance refers to the amounts found in nature. So, for the magnesium 24, it is known that 78.7% of the magnesium found in nature is magnesium 24, and 10.13% is magnesium 25, and 11.17% is magnesium 26. It is now possible to determine the average mass of the element. Simply add the product of the actual mass times the relative abundance for each of the isotopes. In doing so, we will determine the average mass of the element. The first step in the calculation is to convert the percentages to decimals, where 78.7% is converted to 0.787, and 10.13% is converted to 0.1013. And finally, 11.17% is converted to 0.1117. Now, to solve the problem, simply multiply the actual mass, which in the first case is 23.985, times the converted percentage. 23.985 times 0.7870 is equal to 18.88 AMU. 24.986 times 0.1013 is equal to 2.531 AMU. And 25.983 times 0.1117 is equal to 2.902 AMU. Notice that in each calculation, the significant figures were adjusted. In other words, in the first calculation, 1, 2, 3, 4, 5 significant figures is in the actual mass. However, the percentage only contains 4 significant figures. Since this is a multiplication, simply round to the value with the least number of significant figures, which is 4. To find the average mass of the element, simply add the masses calculated from the actual mass and relative abundance for each isotope. 18.88 plus 2.531 plus 2.902 is equal to 24.313. However, in the values that were added together, one value has 2 decimal places, and the other 2 values both have 3 decimal places. When adding values, always round to the number of decimal places that is consistent with the measurement that has the least number of decimal places. In other words, after adding these 3 values, the answer is rounded to 2 decimal places. So the final answer is that the average mass of this element will be 24.31 AMU.